this evening, we want to talk about momentum, continue our discussion of momentum, and specifically, we are interested in something called conservation of linear momentum. Now, conservation of linear momentum is a principle which basically states that the momentum of things, especially in the case we're interested in, during a collision, the momentum before, the total momentum before the collision and the total momentum just after the collision is the same. So when it comes to conservation of linear momentum, we are interested in finding out what is the total momentum just before things collide. Let's take, for instance, in the case of an accident, before things collide, or as we are going to see in some of the examples we have, in the case of a bullet, before a bullet strikes something, we want to work out what the total momentum is before and just after this collision. We use this principle of conservation of linear momentum to find out what the velocities of things are, either before an event happens, like in the case of a collision, or just after the event happens. So basically, that's what we are going to show. So, some objectives: you should be able to state what the principle of conservation of linear momentum is. Then you should also be able to apply this conservation of linear momentum principle to solve certain simple problems, collision problems. That's what you're interested in. We are going to see that there are two types of collisions which you're interested in. There is something called elastic collisions, and there's something called inelastic collisions. So elastic collisions basically are those collisions where before things collide, when you work out the total, you can work out what the total kinetic energy is of these objects before they collide. Then when you also work out the total kinetic energy after the collision. So in the case of an elastic collision, the total kinetic energy before the collision, just before the collision, and the total kinetic energy just after the collision are the same. So in these cases you're going to look at, you need to work out what the momentum of each object is before a particular event happens and what the momentum is just after that event. So you add the total momentum before the event. In this case, we're interested in collisions, and you also work out what the total momentum is just after the collision. Since these objects have got linear momentum, which is just a product of mass and the velocity of the object, it also turns out, like as we have shown before, that an object with momentum, linear momentum, also has got kinetic energy. So if the total kinetic energy just before the collision and the total kinetic energy just after the collision are the same, then such a collision is called elastic. If the total kinetic energy after the collision is less than the total kinetic energy before the collision, then such a collision is called inelastic. So sometimes you have a collision which is elastic. It's rare, but there are examples of collisions are elastic. So we're going to see what that is and how that can be used. So basically that's what the plan is over this lecture and the lecture we're going to have tomorrow. So for this conservation of linear momentum thing to work, one condition needs to be met. Before these things collide, these objects you're looking at, before they collide and after they collide, there has to be one condition which needs to be met. And that condition is that you should not have an external force which is acting on any of the objects in question. So if you're looking at things which are colliding, basically what we are saying is that before these things collide, there should be no external force, there should be no outside force acting on any of these objects. The reason really is because if you have an outside force or an external force, that external force is going to change the velocity of any of these objects we're interested in. So for this principle of conservation of linear momentum to work, there should be no objects that is experiencing a resultant force. If there is no object experiencing a resultant force, then it means that these objects are going to move with constant velocity. So each of these objects which are involved in our collisions, they should be moving with constant velocity for this thing to work. Is that clear? If the velocity is changing because a force is being applied on these objects just before it collides or after it collides, then you can't apply this conservation of linear momentum. So the requirement is that there should be no external force. The microphones we have talked about. Can you switch off the microphones? Christina. Christina Gafulo, can you switch off your microphone? All right. Okay, so what does the principle of conservation of linear momentum say? Okay, it says that the total linear momentum is always the same before and after an explosion or after a collision. When you work out the total linear momentum of things which are about to collide or an explosion, when an explosion happens, the total linear momentum is always the same. It's always conserved. So when you work out the total linear momentum, if things are about to collide, then you work out what is their momentum. You find the total momentum. Then just after they collide, you also work out what is their total momentum. You find that the total momentum will be the same. So that's what conservation means. To conserve is to be the same. So the total linear momentum before things collide and the total linear momentum just after things collide should be the same, is always the same. The same applies with an explosion. When a bomb is planted, this bomb, or whatever it is, it has got a certain mass, but it's not moving. When someone plants a bomb, that bomb, whatever it is, it has got a certain mass, but that particular bomb has got velocity which is equal to 0. So basically, it does not have any linear momentum. Immediately after, of course, this bomb is going to break up into pieces, and these pieces are going to move in different directions. But they will move in different directions in such a way that when you work out the total linear momentum of all the pieces just after the bomb goes off, the total linear momentum always has to come back to being 0. That's what it means when we say that the total linear momentum is always conserved. So when you work out the total linear momentum before an event and just after the event, it has to be the same. So the principle of conservation of linear momentum states that the total linear momenta is the product of momentum of bodies before they collide or explode is the sum of the total linear momentum according to the directions, which should be the same afterwards. So basically that's what I've been saying. To say this principle of conservation of linear momentum tells us that the total linear momentum of bodies before they collide or before an explosion has to be the same as the total linear momentum just after the collision or just after the explosion. And for this to work, of course, we have said that there should be no external force which is acting on the objects in question, because if there's an external force, the velocity is going to reduce, is going to change, whether increase or reduce. So we are interested in two cases. The most important case we are interested in is when there's a collision. So in this case, we are going to look at an example of two objects. Just a minute. Okay, so in this case, we are interested in looking at the case where we've got two objects of different masses, m1 and m2, and these objects, before they collide, they've got their own velocities. So the velocities of these objects before collision, which is the velocity before collision, that's what we are denoting as u. So the velocity of the first object before collision is u1, and the velocity of the second object before collision is u2. So these objects, m1 and m2, before they collide, they are moving at constant velocities, v1 and v2. That's what we are showing. Then after they collide, they move with different velocities. So the velocities after collision will be v1 and v2, and the velocities before collision will be u1 and u2. So what's conservation of linear? Yes?
You said linear momentum is always conserved, but what I wanted to ask is that since isn't linear momentum dependent on force, which force in general can be lost? Because force can it be lost in form of heat?
No, linear momentum doesn't depend on force.
It doesn't depend on force in
No. Force is the rate of change of linear momentum. You only have a force when there's change in linear momentum. So in this case, our objects are moving with the same force, with the same velocity.
Right.
Linear momentum is just the mass of the object multiplied by its velocity. That's all. Force is how fast the linear momentum is changing. Are we clear?
Yes, sir.
Yeah. So in this case, with this conservation of linear momentum, what we are saying is that just before the collision, before these two objects collide, and just after they collide, the linear momentum has to be the same. It's not going to be the same all the time. No, this is just before they collide and just after they collide. So we're saying the total linear momentum just before collision should be equal to the total linear momentum just after collision. So for this condition to be true, we need to put some more restrictions. And how are we going to do that? Well, there are always directions we're interested in. Remember that linear momentum is a vector. So if it's a vector, then we are interested in the size of the linear momentum. We are also interested in the direction of the linear momentum. Since it's a vector and we are interested in direction, we want this condition, for this condition to be true, the one we have here, it has to be true along the x direction. It has to be true along the y direction also. So we need to reinforce this condition of the total linear momentum before collision equal to the total linear momentum after collision. We need to reinforce this condition along the x direction. We need to reinforce it along the y direction. Now, the other thing you have to notice also is that what makes momentum to be a vector is the velocity. The velocity is what is a vector. The mass is not a vector. So if you're going to enforce linear momentum conservation along the x direction, then you need to find out before these objects m1 and m2, before they collide, we know the velocities of these objects. It's u1 and u2. This is before the collision. So you need to find out how much is the velocity of the first object u1 along the x direction, and how much is the velocity of this particular object u1 along the y direction. So you need to know what is the velocity of the first object before collision along the x direction, what is the velocity of the second object before collision along the x direction. That's what we have here. u1x. Yes?
In an example where an object explodes.
We have not yet reached there. We have not yet reached there on explosions. We haven't reached explosions. We are looking at collisions. So I'm saying that you need to know, since you know you have got velocity u1 and u2, this condition needs to be enforced along the x direction. It also needs to be enforced along the y direction. For you to enforce this condition along the x direction and y direction, you need to know the velocity of the first object before collision along the x direction, which is u1x. You need to know the velocity of the second object before collision along the x direction, which is u2x. So that is the velocities before collision along the x direction. You also need to know what is the velocity of the first object after collision along the x direction, which is v1x. You need to know what is the velocity of the second object after collision along the x direction, which is u2x. You will realize that these ones, u1x, u2x, these are just the components of the velocity, the x component of the velocity. So basically what I'm saying is you need to find out what these velocities u1 and u2 are along the x direction before the objects collide, and what these velocities v1 and v2 are along the x direction just after collision. Apart from that is along the x direction, so we need to reinforce this conservation of linear momentum along the x direction. You also need to know what is the velocity of the first object before it collides along the y direction. You also need to find out what is the velocity of the second object before it collides along the y direction. So you're finding the y components of the velocity of these particular masses before the collisions. So you find the y component of the first object, you find the y component of the velocity of the second object, then you also need to find what is the velocity of the first object after collision along the y direction. You also need to find what is the velocity of the second object after collision along the y direction. So you need to have a table of components where you work out for the first object before it collides, what is its x component, what is its y component. For the second object before it collides, you need to find out what is its x component, what is its y component. For the first object after collision, you need to find out what is the x component of the velocity, what is the y component of the velocity. For the second object, you need to do the same thing. You find out what is the x component of the velocity after collision, and what is the x and y component of the second object velocity after collision. Once you do this, then you can reinforce this condition: total linear momentum before collision along the x-axis should be equals to total linear momentum after collision along the x-axis. Now, this is just before the collision and just after the collision. That's what we have here. m1, which is the mass of the first object, multiplied by the velocity of the first object before collision along the x-axis, which is u1x, plus m2, which is the mass of the second object, multiplied by the velocity of the second object before collision along the x-axis. This is the total linear momentum before collision along the x-axis. This which I've highlighted. This should be equals to the mass of the first object multiplied by the velocity of the first object after collision along the x-axis, which is v1x, plus the mass of the second object multiplied by the velocity of the second object after collision along the x-axis, which is v2x. So this bit here, m1 v1x, is the velocity of the first object after collision along the x-axis, plus this other one here is the linear momentum of the second object after collision along the x-axis. So the momentum along the x-axis for these objects before collision and after collision has to be the same. You can also extend this same reasoning to the y direction. Then you're going to say this here is the momentum of the first object before collision along the y direction. That's given by m1 plus u1y, plus the momentum of the second object before collision along the y direction, which is u2y. So this here is the total linear momentum before collision along the y direction. This should be equals to the momentum of the first objects after collision along the y direction, which is going to be m1 multiplied by v1y plus the momentum of the second objects after collision along the y direction, which is m2 v2y here. So we are enforcing this requirement that the total linear momentum before collision along the x direction should be equal to the total linear momentum just after collision along the x direction. We are also enforcing the other thing: the total linear momentum before collision along the y direction must be equal to the total linear momentum just after collision along the y direction. Are we clear?
Yes, sir.
If a collision happens now, then you wait after 1 hour. That particular object might have come to a stop. So it's not that this conservation of linear momentum works after 1 hour, 2 hours. No. Conservation of linear momentum only works just before the collision and just after the collision. Are we clear?
Yes, sir.
Yes.
Sir,
These two equations, they only work just before the collision happens and just after the collision happens. Now, as we have seen also, we have seen that when objects have got momentum, it also means that they've got kinetic energy.
Sir, a second, may I please copy the equation?
Sorry?
The first. May I please copy the equation?
The notes are there. What are you copying?
The equation, the best.
What are you copying? The notes are on Moodle.
The equations are
I'm saying the notes are on Moodle. Go and download the notes so that you don't have to copy anything. Just go and print. Are we clear? So, like I've said, when an object has got linear momentum, we have shown that this object also has got kinetic energy. Okay? However, we can do the same thing sometimes, because these things which are colliding, usually when things are colliding, they are colliding on a flat surface, like on a table and stuff like that. Or maybe it's a cars which are colliding, so it's on a road. That road is flat when the accident is happening or stuff like that. So usually when things are colliding, we assume that there is no change in the height, which means that there is no change in gravitational potential energy. Okay? So sometimes we can work out what is the total kinetic energy before the collision, and what is the total kinetic energy just after the collision. So when we work out the total kinetic energy just before the collision, which means that we have to work out the kinetic energy of those particular objects using this expression here, half mv squared, where m is the mass of the object and v is the velocity with which the particular object is moving. Remember, we assume that these objects are moving with the velocity which is not changing. They are moving with constant velocity. Are we clear? That is the assumption we make when you're trying to apply conservation of linear momentum. We assume that these objects which are colliding, they are moving with constant velocity. It's either some object has got a velocity of 0, or an object is moving with a velocity which is not equal to 0, but that velocity does not change as time passes. So we are assuming that the velocity is the same. So if the velocity is the same, it means that there is no force, external force, which is acting on these objects. Because if there's an external force acting on these objects, then the velocity is going to change. So if we know what the velocity is and what the mass is, we can always work out the kinetic energy of each of these objects. So when we work out the kinetic energies of these objects, we can add the kinetic energies of these objects before they collide, and we can also work out the kinetic energies of these objects just after the collision. In our case, we have mass m1, which has got a velocity u1. This is before collision. We have got mass m2, which has got a velocity u2. So we can work out the total kinetic energy just before collision. Then after they collide, they move out from each other with velocities v1 and v2. So this allows us to work out the kinetic energy just before the collision and just after the collision. So when we do that, we can end up with this expression here. The total kinetic energy before, in this case, is going to be half mu1 squared, which is the kinetic energy of the first object before collision, plus half m2 u2 squared. This is the kinetic energy of the second object. So this whole bit here, this is the total kinetic energy before the collision. You can also work out the total kinetic energy after the collision, which is going to be half m1 v1 squared plus half m2 v2 squared. This bit here. This other bit is the total kinetic energy just after collision. Now, if you do this, then it turns out that the total kinetic energy just before collision is equal to the total kinetic energy just after collision. If the total kinetic energy of your objects just before collision is equal to the total kinetic energy just after collision, then what you have is what is referred to as a perfectly elastic collision. Usually that's not the case. It turns out most of the time that after a collision happens, the total kinetic energy just after collision will be less than the total kinetic energy just before collision. So in that case, which is the most common case, what you're going to have is what is called an inelastic collision. So in an elastic collision, the kinetic energy before and the total kinetic energy before the two objects collide and after they collide are the same. That's an elastic collision. In an inelastic collision, this condition is not met. So when this condition is not met, then what you have is an inelastic collision, and that is the most common type of collision. Are we clear?
Yes, sir.
Okay, so we're going to try to look at what? We'll try to look at some two examples before we conclude today, then we'll continue tomorrow. Okay, so we have an example of a bullet. So an 8-gram bullet fired horizontally, into a 9 kg cube of wood, which is at rest and sticks into it. The cube is forced to move and has a speed of 0.4 meters after impact. Find the initial velocity of the bullet. So we're being asked to find the velocity of the bullet before it hit into the wood. Again, since the bullet is colliding against the wood, basically this is a collision problem. You have to treat the bullet as small as it is as one object which is colliding with a piece of wood which is much larger and gets stuck into it. So basically this is a collision problem. For these collision problems, you have to assume that there is no external force acting in any of these objects. That means that these objects must be moving with constant velocities. Otherwise, if there is an external force, then the velocity of the objects will change. And you have to do other things like that. So in this case, for the bullet, we denote the mass of the bullet to be mb, which is 8 grams. But again, you do not do calculation in grams, so you have to change your 8 grams into kgs, so it will become this. So that is going to give you 0.008 kgs. Then next, the velocity of the bullet before it strikes the wood, we denote that as ub. U as the initial velocity, then b for the bullet. Okay. We do not know what the velocity of the bullet is. That's what you're looking for. Then the mass of the wood, we denote the mass of the wood as mw, and that is 9 kgs. Before the bullet strikes the wood, we are told the wood is at rest, so the wood has a velocity uw, which is equal to 0 meters per second. So we know the mass of the bullet. We are looking for the velocity of the bullet before impact. We know the mass of the wood. We know that the wood was at rest, so its velocity is equal to 0 meters per second. So with this information, we can work out the total linear momentum before impact. So that's going to be the mass of the bullet multiplied by the velocity of the bullet, ub, plus the mass of the wood multiplied by the velocity of the wood. So this is going to give you the mass of the bullet, which is this 0.008 kgs multiplied by UB, plus the mass of the wood, which is 9 kgs multiplied by the velocity of the wood, which is 0. So here I've got 9 kgs multiplied by 0. So this bit here is going to give you 0. And the only thing which is going to contribute to total linear momentum is this bit here. This one here. 0.08 kgs multiplied by UB, which is this one here. That's what's going to contribute to the total linear momentum. The other thing you should remember about what we said about linear momentum is a measure of motion. Linear momentum is a number, it's a physical quantity which gives you how much motion is happening. Okay, so this is how much motion is there. So as you can see, all the motion which is happening before impact is because of the bullet. The wood does not contribute any motion because its velocity is equal to 0. So as you can see, the total linear momentum before impact is entirely because of the bullet and its velocity. After impact, so this is what the total linear momentum before impact. After impact, just after impact, a couple of things happen. The bullet gets stuck in the wood. So the bullet and the wood become one mass. Is that clear? The bullet gets stuck in the wood. So the bullet and the wood become one. So we can denote this combined mass of the bullet and the wood. The combined mass, we can denote it as MB plus MW, and that's going to give us MB plus MW is going to give us a mass of 0.008 kgs plus 9 kgs. So we will have a combined mass of 9.008 kgs. Then we are told that the wood moves off after impact with a speed of 0.04 meters per second, 0.4 meters per second squared. So after impact, this combined mass of MB plus MW has got a velocity V of 0.4 meters per second. So you can work out the total linear momentum after impact. So the total linear momentum after impact is going to be the combined mass of the bullet and the wood multiplied by the velocity. So the combined mass we know is this one, 9.008 kgs multiplied by the velocity, which is 0.4, and we get the total linear momentum just after impact of 3.6032 kgs meters per second. So this is the total linear momentum just after impact. What we have here is the total linear momentum just before impact. Conservation of linear momentum requires that the total linear momentum just before impact and just after impact should be the same. So we are going to equate our total linear momentum before impact, which is this one. This should be equals to the total linear momentum after impact, which is that one. With this thing which are formed here, because we are trying to enforce this conservation of linear momentum, then it becomes possible for you to find out what UB is. Because for you to find UB, we just divide both sides by this 0.08 kgs. So we divide both sides by 0.08 kgs. So we end up with UB, which is the velocity of the bullet before impact, will be equals to 3.6032 kgs meters per second divided by the mass of the bullet, and this will give us a velocity of the bullet before impact of 450 meters per second. Are we clear on how we use this principle of conservation of linear momentum?
Yes, sir.
Okay, so that is an example of how we use conservation of linear momentum in the case where a bullet collides with another piece of wood. You can also have another example here where, example number 2, we have a 16 gram mass is moving in the positive x direction at 0.3 meters per second, while a 4 gram mass is moving in the negative x direction at 0.5 meters per second. They collide head-on and stick together. Find their velocity after collision. So again, we assume that the velocities of these objects are not changing. that the 16-gram mass, its velocity throughout before the collision happens remains at 0.3 meters per second. That the velocity of the 4-gram mass before they collide, its velocity is always 0.5 meters per second. The reason why we assume this is because we have made, there is a requirement that if you're going to use this conservation of linear momentum, the requirement is that there should be no external force, because an external force causes a velocity change. So if the resultant force is equal to 0, then the velocities remain the same. What this thing points out really, what it brings out is the fact that there is direction here. Positive x direction. So if the velocity is in the positive x direction, then this value is going to have a plus value. It's going to be a positive velocity, 0.3 meters per second. The other object is moving in a direction which is opposite. It's moving in the negative x direction. So this velocity, which you have here, is 0.5, because there is direction involved. We have been told the direction it's moving. This is going to be a negative velocity. So we are going to assume that our mass, our 16-gram mass is going to be m1, then our 4-gram mass is going to be m2. So if this bit becomes m1, then this one becomes m2, then this mass is going to be our u1, then this mass is going to become our u2. So basically, that's what we do. So we assume that the 16-gram mass is our m1. m1 is going to be 16 grams, which is going to be our 0.016 kgs. And this mass is moving in the positive x direction. So its velocity, u1, is going to be plus 0.3 meters per second. Then the other objects, m2, this one, 4-gram mass, this is going to be our m2, and we obtain its mass in kgs. That's going to be 0.004 kgs. Then we are told that this object's velocity, this object is moving in the negative x direction. Therefore, u2 is going to be not 0.5 but minus 0.5. The minus here is showing this detail here, that the object is moving in the negative direction. Are we clear? Is everyone clear about this?
Sir.
That if an object is moving in the negative direction, then its velocity is going to be negative. Okay, so with this information, we can work out what the total linear momentum is just before the collision happens. So that's going to be m1, which is the mass of the first object, multiplied by u1, which is the velocity of the first object, plus m2, the mass of the first object, plus u2, which is the velocity of the second object. Mass of the second object plus velocity of the second object. The other thing we are doing here is we are assuming that these things are moving in a straight line. That these collisions, the first example in this one, these things, when they collide, they will move in a straight line. If things collide, then they end up not moving in a straight line, then we have to find out how much is the velocity along the x direction, how much is the velocity along the y direction before they collide and after they collide. Right now, the simple assumption we are making is that when these objects collide, they move in a straight line. Before they collide, they're moving in a straight line. After they collide, they're moving in a straight line. So in this case, m1 is our 0.016 kgs multiplied by the velocity, which this object is moving in the positive direction, plus 0.3 meters per second, then plus u2 is 0.004 kgs multiplied by the velocity of u2, which is minus 0.05. So you can see in this case that when you are trying to work out how much motion is happening, if objects are moving in different directions, one object is moving in this direction, the other object is moving in the opposite direction, there is a minus here. This minus here reduces the total linear momentum. Yes, there's a question?
No, I want to ask.
Yes.
It's always that they are going to tell us it's moving in the negative x direction.
If we don't tell you, then you have to assume that they're moving in the same direction.
It's always that they are going to.
If you are not told, if I just say they're moving at 0.3 and 0.5, you assume that they're moving the same direction. But we have to tell you that one object is moving in the opposite direction. This negative direction here, it simply means opposite. I can tell you an object is moving in this direction, the other object is moving in the opposite direction. If I say opposite or negative, it means the same thing. So sometimes you might find negative being used, or you might find opposite being used. Are we clear? Negative and opposite, they mean the same thing.
Yes, sir.
Yes, in this case. So when you work out the total linear momentum, in this case here, you see that this is how much linear momentum you have. 0.0028. This is a very, very small amount of linear momentum. The reason why it's small is because these objects are moving in different directions, and linear momentum is a vector. So that the fact that these objects are moving in opposite direction reduces how much motion is happening. Okay, so this is the total linear momentum before collision, small bit. Then we are told that the first mass, which is a 16-gram mass, and the 4-gram mass, they stick together and move. They stick and move together. So if they stick and move together, again, this is similar to what happened before. It means that we have a combined mass of M1 and M2. So the combined mass of M1 and M2 is going to be M1 plus M2, which is this one here, and they move together. So there is going to be, they have some velocity after the collision. So that's going to be V. And this is the velocity you're looking for, V. This much we can work out, the combined mass we can work out because we know the masses M1 and M2, that is 0.016 kgs plus 0.004 kgs. So this bit we can work out. This one here, this one we can work out, multiplied by V, and the combined mass is just 0.02 kgs. So 0.02 kgs multiplied by the velocity V, which is the velocity with these things move together after the collision. So before collision, this is a total linear momentum. Just after collision, this is the total linear momentum. We assume that these velocities don't change. So since we have got the velocities before collision and after collision, we can enforce conservation of linear momentum, the fact that the total linear momentum is always conserved. So that means that the total linear momentum before the collision has to be equal to the total linear momentum after the collision. Before collision, the total linear momentum is this much, 0.0028 kgs meters per second. Then after collision, it's 0.2 kgs multiplied by V. So we can divide both sides by 0.02 to find out what V is. So in this case, V is going to be equal to 0.0028 kgs meters per second divided by 0.2 kgs, and this is going to give us a velocity V which is equal to 0.14 meters per second. So the velocity after collision is 0.14 meters per second. This velocity, as you can see, it's not negative. This velocity is positive. That's the first thing you notice here. This V, the velocity of the combined masses when they stick together, M1 and M2, when they stick together, they move with a velocity which is positive. This means that when they stick together, they move along the positive x direction. Are we clear?
Yes, sir.
When these two objects, the bigger mass, the 16 grams, when it collides with the smaller mass, the 4 grams, moving in the opposite direction, these objects, when they collide, they will move in this direction in which the bigger mass was moving, which is a positive direction. However, something happens. The bigger mass was moving with a velocity of 0.3 meters per second. This other one was moving the velocity of 0.5 meters per second. But when you look at the size of the velocity, you see that the velocity reduces. The velocity reduces, it becomes 0.14. It reduces by slightly more than half for the first object, the 0.3, the bigger object. The bigger object was moving at 0.3 meters per second, but after collision, it ends up moving with 0.14, which is about half the velocity it had before. So this is something to notice here. So when you've got a big object colliding against a smaller object, usually things after the collision, things tend to move in the direction of the bigger guy. But of course, the bigger guy is going to experience a reduced speed. Is that clear? Any questions?
Yes, it's clear.
Okay, any questions? Okay, so if there are no questions, we'll end here for today. Of course, the recording has been done. It's going to be put on YouTube.
Next week.
Sorry?
But not going to be the one taking us. Now, no, sir, I have a question.
Yes.
My question is that. Hello, sir.
Yes, I'm hearing. What's the question?
Since you have said that next week, my question is that since you have said that next week you are not the one going to be taking us, then
Yeah.
the one who is going to be taking us, is he going to be using the same link for our classes or what? Or
No,
not?
we're going to update the links. I will update the links. He has already sent me the links he wants me to use, so I'll put his links there.
Oh, okay.
On your end, it will look like it's just a normal link, but I'll update the links in the background.
Oh, okay.
Yes.
Okay.
Any other question?
Thank you very much.
You're welcome. Any other question?
Sir,
Yes.
a question about how the test was like. It was like a multiple choice one. Like, is it going to be like that even like for the future tests that you're going to be having?
Yes, it has to be like that because there are too many. You have multiple choice things. You're just too many. We can't afford it. We can't manage to mark your things, all of you. So it will be multiple choice. It will be like that. Basically, that's what it's going to be like. Yes.
Even the final exam. Sir, even the exam.
Yes, even the final exam. We don't have a choice because there is a timetable to these things. You have to move to second year, and we only have we are usually given less than 1 month to mark your things. So if you're going to mark 4,000, I don't know how many you guys are. You're like more than 3,000. If you're going to mark 3,000, we can't mark long things. We have to try to make it as short as possible, while trying to ask you.
So you mean it will still be multiple choice even on the exam?
Yes. You have to work out things,
Okay.
then you choose the answers. That multiple choice requires you to work out something on a rough paper. So you'll be given rough paper, then you work out, then you see what the answer is, then you choose. Are we clear?
Yes, sir.
Yes.
Yes, sir.
Any other question before you go? Yes.
Our test results disappeared on Moodle. What happened?
Those things will be fixed, John. Those things, they will be fixed. Yeah. Okay. So like I said, the recording will be uploaded to Moodle. Tomorrow we are meeting. So we're meeting I think at 12, right?
Yes, at 12.
Yeah, we're meeting at 12. Okay. All right. Thank you very much. See you tomorrow.
You're welcome.